last class we started looking at Leeson's model, so let's quickly review this again. So we said primarily this is more of an empirical model. So the idea is you pick up an oscillator and you measure its phase noise, see what it looks like, right? And then you try to explain it using a model. And what you find is that the phase noise has three distinct regions. There is a region very close to the oscillator where the phase noise falls at minus 30 dB per decade as a function of the frequency, as a function of the offset frequency from the carrier. After some time, the noise starts going at 20 dB per decade, and finally it flattens out. Okay, so you see three distinct regions in the phase noise characteristic of any oscillator. I am showing only the one-sided spectrum. Obviously, the noise of an oscillator will have that left-hand side also. Okay, left-hand sideband. Obviously, this is also on a log scale as I have drawn it. Okay, it's on a log scale. The y-axis is in dBc per hertz. The x-axis is in log of the frequency. Okay, now we need to find out a way to explain this, the existence of each one of these, and explain what the noise level is, the actual value, and see if it actually makes sense, right? So we said let's assume that the energy transfer block is actually noiseless. Okay, so let's start off with that because that is really the easiest way to analyze this, simplest way. Let's assume that's noiseless, and let us say there is some noise across the RLC tank, and to start off with, you can even say that all the noise comes only from the RLC tank. This could actually be the case when you actually have a very low Q tank. When you have a very low Q tank, the parallel resistance of the tank will be very small, and the noise current from the tank will be very large compared to the active portion. Okay. Now, then what we did was we wrote out explicitly the impedance of the tank as a function of the offset frequency delta omega. And when we did that, we reduced it to this form, but more importantly to the magnitude is a function of the resistance of the tank, is a function of omega naught, is a function of Q, and is a function of delta omega. Okay, these are all important factors which will affect the impedance of the tank as a function of delta omega. Then we said that the voltage noise is actually the voltage squared noise is the current squared noise times the square of the impedance, and we got an expression which looks like this. Then we said there are only 2 degrees of freedom for the noise, which is the amplitude of the noise and the phase of the noise. So therefore half of this noise appears in the phase of the signal we are interested in. So the actual phase component is 2 kTr times omega naught by 2q delta omega the whole squared. Then all we have to do is stick this inside our fundamental definition of single sideband noise, which was 10 log of the noise power over the signal power. In this case we have the noise square voltage over the signal voltage squared, okay, to get the phase noise. And we get something which looks like this. Okay, all well and good. So now we need to go back and look at Leeson's model, and but before we do that, what we find is if you just take this into account, just this expression alone, it explains a minus 20 dB per decade region, but it does not explain anything else. Okay, so obviously noise from thermal noise getting filtered by the tank probably explains part of it, but not all the noise. It does not explain the other 2 regions. So that is why you actually go back and have to tweak this model to actually come up with something which explains all 3 regions. And that is how Leeson came up with his model. And the actual expression for Leeson's model was given in class last time. So there is something which looks similar to what we see before. So we get a 2 kT by P sig, we have seen that before. We got omega naught by 2q delta omega the whole squared, we have seen that too before. However, there are a couple of other modifications. One of them is these 2 expressions to actually give you the flat noise as well as the 1 over f cubed region. Correct? We have these 2 regions. Apart from that, we also have this other factor f, and that is another empirical factor to try to explain excess noise. Okay? So the question is, you put in all the other items and suddenly you build your oscillator and find that it has more noise than what you expected, 3 dB more noise or 4 dB more noise. Okay, so then you need to figure out why it has excess noise. Of course, one quick way to go about this is to actually measure it for a number of oscillators and try to see if F is constant. Okay, but as it turns out, F is not constant. Okay, unfortunately, F is a strong function of your design parameters. Okay, so the nice thing about this model is that it really explains, or tries to fit in the existence of a minus 30 dB per decade region, minus 20 dB per decade region, and a flat noise region. It has this F factor to actually explain any excess noise. Now, the really strong factors which people saw in this model is that it explains the dependence on the Q of the resonator. Okay. So if you actually double the Q of the resonator, what happens? What happens to the phase noise? Right? So this analytically explains the noise as a function of the Q. Okay, especially in the 1 over F squared region. Similarly, the dependence on the omega naught, on the carrier frequency. If you keep everything else constant but double the frequency, what happens to the phase noise? So both of those factors, this model really explains very well. Okay. However, obviously it's an empirically driven model, right? So we want to get some design insight into, or more importantly, we want to say, apart from the Q and the omega naught, there are other factors we now have in play, right? Especially the active device. Right? Now, the cross-coupled pair, we have, we have said that the GM of the cross-coupled pair should be large enough such that you have a startup gain. But does it tell you whether you need a startup gain of 3 or 5 or 10 or 100 or what? Right? Or just 1.1? Right? And what impact does that have on noise? Right? If you change the GM of the transistor, what impact does that have on noise? Right? This model does not give any of that. Okay. Now, you have a couple of more sophisticated models. So, okay. Actually, there are several more models, more complex models, but we'll discuss 2 of them here, or rather we will discuss 1 of them, but we'll mention 2 of them here. The first one we'll mention is the Abidi model. Okay, so the reference I'll give you this. It's called Physical Processes of Phase Noise in Differential LC Oscillators. Okay, and it was presented at the IEEE CICC in 2000. Okay, so what they did was they took the specific case of the LC oscillator, because that is really, in fact, even by 2000, that was fast becoming the most popular integrated circuit oscillator for obvious reasons, right? Fairly easy to design, right? In fact, more importantly, it's very current efficient. Okay. Also, it gives you differential outputs, which most discrete oscillator or earlier oscillator architectures did not give you, or you had to take special effort to actually get differential outputs. Okay. So now, very specifically, they want to analyze and they want to analyze noise for differential LC oscillators, primarily cross-coupled oscillators. Okay. Now, suppose we are actually designing this, and you actually go back to Leeson's model. What is the fundamental drawback of Leeson's model? What is the fundamental thing that is glaring at you? Correct. But primarily, actually in his model, the only empirical factor is F. Right? The other factors are factors which he has put into to try to get a 1 over F cubed and a flat noise region. but primarily the empirical part is F, right? So if you take a differential cross-coupled LC oscillator and figure out a value for F, right? Figure out a value for this F, that itself will go a long way towards helping you figure out what the excess noise number is, okay? And then you can see if it is repeatable. So really that is the main contribution of this work, is to determine expression for F. Okay? And if you remember, if you go back, we actually did some noise analysis for the active mixer. Okay? So this particular analysis follows a very similar procedure. Okay? If you remember, what we did was we took the differential pair, we took the noise, separated into pulses and so on, and we got three expressions depending on noise from different sources. The same procedure is followed in this work also. I'll give you the final expression because really we want to move on to the third, the other sophisticated model. But what they figured out was the expression for F is 2 plus 8 gamma RIT over pi V naught plus gamma times 8 by 9 GMR. Okay? Where of course V naught is 2 by pi ITR for a cross-coupled NMOS oscillator, right? But really they actually let's not even put that in here. So really they came up with an expression for F. Okay? So in other words, if you actually want to go out and build an oscillator and want to figure out what this excess noise number is, you now have an analytical expression. Okay? So this will tell you what the, if you increase GM of the transistor, for example, this will tell you how much F is increasing. So all well and good. This is also based on? Well, this is not strictly no. Strictly this is not based on the LTA. Yes, that's right. It's more of an LTV base, but not an explicit LTV. Okay, and you'll see why. Okay, the reason is this. What the basic mixer model, if you go back to your active mixer model, what that told you is, it told you if you have a noise voltage, it tells you that it actually modulates the point when the differential pair switches. Okay. Now, apart from that, the basic transfer function from noise to phase, apart from that particular aspect, is not fundamentally seen as time variant. However, you will see that the third model explicitly makes that time variant and starts off from first principles to actually figure out what the noise should be. Okay, so let us move on to the third, the second model, which is the Hajime-Reilly model. Okay, so to look at this model, we need to kind of take a step back and try to understand what this process is, what happens when you actually have noise being injected into the tank, and how it actually manifests as the output phase. Okay, so what they did was let us say you take an LC oscillator, right, the output of an LC oscillator. Now what happens if you look at this LC oscillator? This is the output of an ideal LC tank. Okay, I have an LC, and if I have some initial charge, it will be oscillating here. Now what I have said is, I have a noise current being injected into this tank. Now the noise current obviously is continuously being injected. However, the response of the tank itself is different depending on when the noise is injected. For example, if I were to inject some noise at this time, or let me draw it slightly differently. If I actually injected some noise, or think of it as a noise charge, okay, being injected into this tank. right? Well, let's say at that particular instant it's an impulse charge. Okay, what happens to that noise charge? Does it go into the inductor or the capacitor? Into the capacitor. Why? High frequency. No, this has nothing to do with high frequency. No. This is at the frequency of. See, we are saying this is at the resonant frequency, right? There is no talk of high frequency where the capacitor is lower impedance or anything else. Okay. So what? But it doesn't have to be at the voltage peak. Let us take at any point. At any point, I am injecting some IN, or you can look at it as QN charge. It's an impulse. A charge, I am dumping charge, it's an impulse current. Okay. If I have an impulse current going into an LC tank, how much of it can go into the inductor? If any of it goes into the inductor, you will see an infinite voltage across the tank. So the charge has to get deposited onto the capacitor. Okay, all this charge, impulse charge, has to go onto the capacitor. Okay, what happens if this impulse charge goes onto the capacitor? You will get a voltage, an extra voltage being developed across the capacitor, and therefore the voltage across the tank will change, irrespective of which point of the time axis this actually happens. Okay, first, well, let's start off with the peak of the sinusoid. What do you think will happen? So, of course, originally it was following this trajectory. Yes. No, of course not. If you have a parallel LC tank, you have to model the noise as a current, right? Of course, because if you model it as a voltage, you are basically, when noise is not there, you are shorting out the tank. That is not the real case, right? Okay, so then what happens? I reach the point when noise is injected, and now the voltage of the tank just increase. What trajectory does it follow after that? Correct, but suppose I am doing it at the peak. What will happen? Okay, so let me ask you in a different way. Suppose the amplitude will obviously change, so that's why I have actually increased it like this. But after this, I want to see what will happen. So let us take a step back. Obviously, this is some V peak, right? I started off with some V peak earlier. I get this phase, right? It's an ideal LC tank. Suppose I had started off with V peak plus delta V. What trajectory will it follow? So initially, I started off with some V peak. Correct? It follows this trajectory. Minus V peak to plus V peak. Correct? Correct. Any charge injected at which increase, so at this point, right, all the charge is only on the capacitor, inductor has no current. Correct? All the energy is stored in the capacitor. It is as if, it looks exactly like my initial condition when I actually started off with some V peak. If I had started off with V peak plus delta V, would the phase of the oscillator have been any different? No. Right? The peak charge has no relation with the phase of the oscillator, and therefore all I'll see is, I'll see an increased amplitude or a decreased amplitude depending on the magnitude of this charge, depending on the sign of this charge, but the phase of the oscillator will remain exactly the same. Okay? So if I were to actually redraw this, I'll actually see something like this. Something like this. Right? The zero crossings will not be affected at all. Okay? Zero crossings will remain the same. The only difference is, I'll go with V peak plus Vn. Correct? Okay? Suppose let us take the same oscillator. Now I am going to inject this Qn, this noise charge, at the zero crossing. What happens? the phase of the oscillator will be fundamentally shifted. Okay, because the zero crossing was supposed to happen here. Okay, but what will happen is now the zero crossing will happen like this. Right? So what you find is, this is obviously a very important point which was not seen by others earlier. Okay, the LC tank is fundamentally sensitive to when you inject the noise. Okay, that is why it is a time variant system. Okay, because apart from the observation time, you can actually define a second time, maybe tau, when you actually inject the noise. Now, the response of the system is a strong function of tau. Okay, so if this was delta of tau, okay, the response of the system is a strong function of tau, therefore it is a time variant system. So now what we need to do is figure out for this oscillator what this time variant response is. So now we need to find out the response of the system. Now the nice thing about this, okay, there are a couple of nice things. So first of all, apart from it being a time variant system, okay, the response for noise, okay, is always going to be a small signal response. Okay, because these impulses are much smaller compared to the actual amplitude of the tank. Okay, therefore you can actually define an impulse response of the system. Okay, however, you have to remember that the impulse response of the system will be we need to find out if there is some dependence on the time when the noise is injected and so on. So let us start writing out the expression for the impulse response. So okay, so since linearity still holds, we are going to write out an impulse response very specifically for phase. Okay, we want to find out how the output phase changes as a function of your input impulse. So we'll define h pi of t comma tau. So I'm going to write this factor gamma, okay, gamma of omega naught tau. I'm going to explain what that is, by Q max. Okay. So this is the impulse response for the phase, okay, when you have for the system, okay, for this LC oscillator. Now what are these factors? Q max, so this is the maximum. So the main idea is to normalize this impulse response to the amplitude of your particular oscillator. Okay, so that is why you have this factor Q max, which is the largest charge displacement across the capacitor. Okay, the peak charge displacement across the capacitor. Okay. Now I'll just explain, just give me a minute, I'll explain what this gamma of omega tau is. This gamma of omega tau is, okay, is called the impulse sensitivity function. Okay, so this represents the sensitivity of the system as a function of tau. Okay, so depending on when you inject this impulse, the response of the system is going to be different. We've already established that. So this impulse sensitivity function actually represents that change of the response of the system. Is that clear? It is a function only of tau, not of t. Right? Okay, very good question. So t is the observation time. Observation time variable. Tau is the point at which the impulse is injected into the tank. sorry, I should have defined that earlier. Tau is the point where you inject the impulse. The t is the observation time. Okay. Now, okay, so this gamma is the impulse sensitivity function. Now, if you had to write the output phase, okay, it would have this expression. Okay, if you had to write the output phase as a function of the input current, input noise current, IF tau is now the noise current. Earlier that was just the impulse response. This is the expression for the phase itself. Okay. And this is the total phase at t. Okay. Why do we integrate from minus infinity to t? There is obviously nothing we have already established that there is nothing inside the oscillator that restores the phase of the oscillator once it is changed. Right? So you will have to look at all the phase disturbances from minus infinity to your present time and all the phase changes which have happened, and you need to sum over that, right, to find out your present phase. Okay, so you have to integrate this from minus infinity to t. Now, what is this ISF function? Okay, so assuming you know all of this, you can do this. But what is this ISF function? So as it turns out, for many systems, this ISF function is okay. Actually, let me draw it out, and you'll see. And then we'll see what it probably is. Okay, so let me draw cosine omega t function. Okay, we are going to look at two cases. This is an LC oscillator. This is a ring oscillator. Okay, this obviously this theory is independent of what kind of oscillator you are using. You can use this for ring oscillators also. Okay, what does a ring oscillator look like? So maybe like this. Something like this. Ring oscillator output is a square wave. Okay. So let us first start off with this LC oscillator. So some V0 cos, let's say just cos omega t, right? So as it turns out, it's a minus sine omega naught t curve. Okay. Similarly, if you had to do the same thing for a ring oscillator, okay, there is a slight difference for the ring oscillator. For example, you can do the same analysis for ring oscillator. What happens if I inject noise here versus here? So what do you think the ring oscillator curve will look like? Definitely you will see something similar. At the zero crossing, it will be most sensitive. But what you will find is, for a ring oscillator, the behavior is slightly different, because once the output saturates, any noise will not change the phase at all. Okay. So if you actually look at a ring oscillator, you will see something which looks like this. Okay, you will see pulses. So the ISF looks like pulses right at the zero crossings. But fundamentally, for most systems, the ISF, first of all, looks like the derivative of the output waveform. Okay, that you should be able to see. You have a cosine, it's minus sine. You have a square wave. You have impulses at the zero crossings. Okay, and you can theoretically show that it is the derivative of the output waveform. Okay, in the end, I'll give you the reference to the paper. You can go ahead and read it. They have shown that it is the derivative. Okay. But in most cases, you may worry that you may not have perfect sinusoids or perfect square waves. So really it is best derived from simulation. When you are designing it, it's very easy to actually start injecting pulses, sweep this and figure out what the impulse sensitivity function is. Okay, so this is best derived, best obtained from simulation. Okay, this is best obtained from simulations. Okay, so now let us say we have somewhat understood what this impulse sensitivity function is. Now, what else do we know about this impulse sensitivity function? We know one other point. Let's go back. I said it's the derivative of the output waveform of the oscillator, right, of the voltage waveform. What does that mean? What do you know about the voltage waveform of the oscillator? It is periodic, right? So this derivative should also be periodic, okay, at the same frequency as it so turns out. So this delta omega, this gamma is periodic at 2 pi, okay, because I have written as omega naught tau. It's periodic at 2 pi, at the rate of 2 pi, which means, what do you know for a periodic function? You can expand it as a Fourier series, right? So I'm going to expand this as some C0 by 2 and sigma of n equal to 1 to infinity Cn cos n omega naught. Since I'm using tau, I'll use tau here. Okay, cos omega naught tau plus theta n. Okay. Okay, I'll write it down as a Fourier series like this. Now, how do I proceed from here? How do I proceed from here? Well, all I have to do is write out the expression for phase, okay, as a function of now this Fourier series, because now I've actually expanded this Fourier series as a function of n omega naught. Okay, so now I'm going to write phi of t as 1 over q max into C0 by 2 integral minus infinity to t I of tau d tau, okay, plus okay, I'm going to move the next expression to the next page, plus sigma equals n 1 to infinity Cn minus infinity to t I of tau omega naught tau d tau. Okay. Now, what this gives you is the response for a given noise current, okay, to the phase. Obviously, if you want to look at the actual sidebands of the oscillator, what you really have to do is look at the transfer function from the phase to the sidebands, okay, because this sideband, the actual oscillator VO of t, is actually going to look something like cos of omega naught t plus psi of t. Okay, so now you need to see, if you take some random phi of t and put it inside an oscillator, put it as the phase of an oscillator, what do the actual sidebands look like, right? So now you want to split this cos omega naught t plus phi of t into its sidebands, right? So what you're actually doing is doing the response from, okay, so you're actually going from in of t is okay, okay, to phi of t to the S is the spot noise. Okay. Now, of course, going from here to here is fairly straightforward because this phi of t is a small signal variation. Okay, this noise is expected to be much smaller. Therefore, going from here to here has a very standard approximation. Okay, which you can read up. I'll put it up on the class notes. But the really important thing to note, okay, is this. If you actually go back to this expression and look at this, look at this. This particular portion is what we are interested in. Okay. If you want to look at the noise at any frequency, okay, you will have to use this particular expression to figure it out. So let us quickly do that. So let us say I am looking at I am looking at some current at m omega naught plus delta omega. I am looking at the noise current at offset delta omega from some m omega naught. Okay, I want to find out how that noise affects my noise at the offset of delta omega from my fundamental omega naught. Right, that is what I want. Okay, anyways, go back and look at the lecture and I'll put up the complete notes. You can take a look at it. I am coming to the fundamental point of why we are looking at this. Right, the difference between your linear analysis and your time variant analysis, go back to your mixer. The noise at any frequency depends not only on the noise sources from that frequency, but from noise sources at multiples at harmonics of the fundamental frequency of the system. Do you remember that? For the mixer, you had what is called folding of noise from higher harmonics down to the frequency of interest. You see the exact same thing here. Okay? The reason is, if you go through this integration, okay, you substitute some in of m omega naught plus delta omega. Okay, that will give you a component only for n equal to m. Okay, you will see a component of it come down to delta omega. I hope you see that it's just a product of two cosines, right? And since you are having a summing function, for n not equal to m, it will be orthogonal. You will get only 0. For n equal to m, you will get some cos m omega naught tau times cos m omega naught plus delta omega. The product of these two will give you a component of at delta omega. That is the important point to see. Okay. Okay. So the fundamental point to note is that if you actually had noise which looks like this, so in squared by delta f of omega. Okay, if you actually had noise which looks like this, okay, and omega naught, okay, sorry, okay. Okay, if I have omega naught to omega naught and so on, I have offsets of delta omega from each one of these guys. Okay, and in fact, from DC also, if I look at the response for phase, okay, let us say it looks something like this, and I am interested in the response at some delta omega. Okay, it has components arising from not only delta omega but from each one of these components, okay, depending on the value of Cn. Now the lucky thing is that this value of Cn actually, as you keep increasing, the harmonic factor you're looking at, the harmonic you're looking at, even though the broadband noise, current noise stays the same, the Cn factor keeps reducing. Okay, and really the Cn factor tells you the harmonic content of gamma of the ISF. Okay, the good thing is that for most cases this content keeps reducing, so you actually get a finite amount of noise. However, this also tells you that noise from delta omega, from an offset delta omega is not only from, the phase noise at delta omega is not only from noise at delta omega, but it's from other noise sources also. This actually tells you why you need that extra factor F in Leeson's model, right? If you only had a linear model and try to look at it as just a current noise from the tank being filtered by the tank, okay, that will not take into account this portion of the noise. Okay, it will only give you this portion of the noise, right? It's exactly like a mixer. If you remember, even in a mixer, you had noise components arising from noise sources which are not at your frequency of interest. This is obviously another effect of any time variant system, right? Okay, so that is the fundamental, I guess, the response of the LC oscillator to noise. I'll put up the full, the complete expressions, the complete notes which I have written up. Just one more point, okay, before we finish up, and then just take 5 minutes for the feature evaluation. But actually two things. So first of all, if you actually take this 1 over f, this particular noise, and take this broadband current noise and apply it to this, you actually get a result and you can compare it back with your LTI analysis. Okay, and you can try to compare, see if they are comparable or not. Okay, that is number one. Number two, we now need to find an explanation for the existence of this 1 over f cubed region, right? As it turns out, this particular noise theory also explains the existence of 1 over f cubed noise. I'll give you the result for the 1 over f cubed. Okay, first of all, the noise, the corner, the 1 over f cubed corner is not equal to the 1 over f corner of the device, or of the devices that you are considering. This happens to be 1 over f times gamma DC by gamma RMS squared. Okay, it has an expression like this. It of course depends on the impulse sensitivity function. But the interesting thing is, if you want to decrease the 1 over f noise, the important insight is that apart from decreasing, making your fundamental devices larger, you can also do one more thing, which is to reduce gamma DC. Okay, what is gamma DC? Gamma DC represents how symmetric your waveform is. Okay, if your waveform, fundamental output waveform was extremely symmetric, it had equal rise times and equal fall times, what you will find is that gamma DC should be very close to 0. Right? Which means your 1 over f noise, upconverted 1 over f noise, to create this 1 over f cube spectrum should also be very small. The more symmetric your waveform is, the more symmetric gamma will be. In our case, we are looking at a sinusoid. Take a simple sinusoid. Let us say it is not exactly a sinusoid, but something which looks very close to a sinusoid, but maybe the zero crossing is slightly different. Okay, or maybe the rise time fall time is slightly different, which is definitely very possible, because if you take some of these oscillators, let us take the cross coupled LC oscillator. Okay, you have something which the discharging of the node when the NMOS turns on quickly is very fast, is decided by how strong the NMOS is. The charging up of the node just happens through the inductor from VDD. Fundamentally, it's not symmetric. If you take a complementary oscillator, NMOS PMOS oscillator, you actually have a way to make it symmetric. Because if you make the pull-up response of the PMOS the same as the pull-down response of the NMOS, you try to make it very close to equal strength, you will get a very symmetric response.